Okay, maybe we should get started. So I'm presenting the next in the fMRI F summer um, talk series, and it follows on actually pretty much from Vinay's talk on Monday. My name's Andy Derbyshire, and I also work as a staff scientist in the functional MRI core. Okay, so today's talk is supposedly advanced MRI and fMRI acquisition methods. Okay, so the outline of today's talk is basically I'll quickly zip through some of the stuff that Vinay presented, partly just to kind of refresh you, and partly so I can present it in my own way because I'll be building on top of it, and I want to kind of introduce the notation in kind of the same way that I would normally present it. And then I'll move on to a little bit more deeper discussion about MRI imaging tools and techniques, case-based trajectories, and image acceleration, and wrap up with some discussion about contrast manipulation. Okay. So basically, MRI is based on nuclear magnetic resonance, and this is an effect due to the intrinsic spin of the nuclei of certain atoms, and in particular, we're looking at the hydrogen nuclei of water molecules, which we tend to refer to as protons, but obviously they're not kind of just free protons, they're part of water. And in the presence of an external these nuclei have spin, a property called spin, and in the presence of an external magnetic field, the nuclei behave like ensembles of nuclei behave like little magnets, and they can absorb and re-emit electromagnetic radiation at a specific resonant frequency. So the resonant frequency omega equals gamma b, and this is pretty much the fundamental equation from which all the stuff I'm talking about today comes from. So omega is the angular frequency, gamma is the sort of constant that relates it to the magnetic field, and b is the magnetic field. So if it increases the magnetic field, the frequency goes up. So obviously the angular frequency is 2 pi the regular linear frequency. So that's a pretty simple relationship. Okay, so for protons or hydrogen nuclei, gamma is about 42 megahertz per Tesla. And so that means that at 1.5 T, we have something like 63 megahertz. So we expect signals around 63 megahertz. At 3 Tesla, it's about 127, and at 7 Tesla, it's around about 300. Okay. Now, if we consider what's called an ensemble, which is basically like a bunch of water molecules together, we can sort of get away from the quantum mechanical stuff, and we can treat it in what's called the vector model. And for this, we end up with the magnetization creates the main magnetic field B0 creates a magnetization vector M, which is a kind of three-dimensional vector in general, mx, my, and z. But at equilibrium, when you introduce it into the magnetic field and you leave it and you let it get to equilibrium, basically it's all aligned along the B0 direction, which by convention we consider to be the z direction. So this is basically along the Bohr magnet, and the magnetization is it's basically like in every voxel you can think of it as having tiny little bar magnet of magnetization within every voxel or even subparts of a voxel aligned along the main magnetic field. And it's kind of worth noting that the magnetization M0 here, which should be on a separate from this underbar, is basically proportional to B0. And so therefore, one of the reasons why we like to scan at higher fields is we end up with more our magnetization M is bigger when we go to high fields. And it turns out that it's not only actually a linear relationship, it turns out our signals are actually more like squared, but I'll come back to that later. Right now, the magnetization itself, it goes like the linear B field. Okay, so here's another mistake in slides. This should say in the lab frame at equilibrium, and the M0 is aligned along Z, which is our B0 direction. Okay, so then if somehow we could get the magnetization away from the B0 direction, and so it was tipped at some kind of angle here. What we'd see is, because it's a little spinning magnet in a magnetic field, we'd see it precessing around the main magnetic field like this, and that precessional frequency would be omega. Okay, so this is kind of like how a spinning top works. So if you had a spinning top and you have it spinning and you tip it away from vertical, which is a gravitational field, which is analogous to the magnetic field here. If you tip it away, the spinning top actually rotates around the gravitational field, which is considered vertical. Okay, so basically we have the same phenomenon here. You saw this yesterday. So when we see it rotating with angular frequency omega equals gamma b. So in general, though, when we're thinking about things like this, it's convenient to work in a lab frame of reference, so the frame itself is now rotating. And that means the magnetization, instead of spinning around like hundreds of megahertz, which is difficult to deal with, you basically can think of it as the magnetization is now kind of frozen in place. And this is just one example now, so that would mean that this x and y are different from the x and y in the previous slide, because this is the lab frame, and this would be in the rotating frame. So this x and y are spinning with respect to the magnet, and the z direction stays the same, of course, because it's still along the bore of the magnet. Okay, so now in the rotating frame at equilibrium, let's say that we have our magnetization here. We're in the middle of the magnet, we've left it for a while, it's fully relaxed, we're at thermal equilibrium, so we've got this magnetization vector m0. We apply a B1 magnetic field. We're in this rotating frame, so we apply this B1 magnetic field along the x direction, which, as we said, is actually rotating in practice. But let's say we apply a little constant B1 here. Now, as far as our magnetization is concerned, this situation is kind of not dissimilar to how it was here. In fact, the magnetization wants to rotate around that B1. So what happens is the magnetization starts tipping like this. Well, actually, it should probably tip the other way, because the way I've written the equation, but we'll let that go. So the magnetization wants to rotate around with this new B1 magnetization, this new B1 magnetic field towards the y direction. And so this is how we can get our excitation done and tip the magnetization away from the main B0 field. We have to apply a B1 field in the x direction in the rotating frame. Now, that looks like a constant B1, but it's, of course, it's in a rotating frame, so it's actually spinning with respect to the main magnet. And it's spinning, which means that basically it's oscillating in the x direction and it's oscillating in the y direction. So that's why it's considered to be an RF field, because the B1 is basically it's basically a magnetic field that's oscillating at hundreds of megahertz. So what we can do is we can apply that B1 field, and then turn off the B1 field when it reaches the appropriate flip angle with respect to the z-axis. And because omega equals gamma B1, if we know what our B1 is, we can just figure out how long we need to leave it on to get the appropriate theta, the angle of excitation. And we could let it go all the way down to the y-axis, to the transverse plane, or send it even further down and invert the magnetization, or even bring it right round and bring it back up again if we wanted to. Okay, so eventually when we turn it off, the magnetization eventually starts to precess, just like as we discussed before, and then it gradually relaxes back to equilibrium, which means that the length of this vector so this magnetization ends up coming back towards B0, but it doesn't just rotate back the same way it came down. Basically what happens is that the x and y components decay back towards zero by a process called T2, and the mz component returns back to the full length by a process known as T1, relaxation. So mz here is referred to as the longitudinal component, because it's the component along the magnetic field, and mx and y and my are transverse to the main magnetic field, and they're known as transverse components. So the other thing to know then is that the signal that we see during MR, it's very hard to detect mz directly. So what we basically end up picking up in our receiver coils is proportional to the transverse magnetization. And so what happens is if you consider this magnetization at some arbitrary position like this, mx, my, mz, we only get a signal that's proportional to the mxy component. And we consider that generally to be a complex number, which is mx plus my. And what we really have is, of course, in the lab frame, what's happening is that's like a little component of the magnetization along this direction, but in the lab frame, because this is still a rotating frame, is actually spinning around and around as this thing processes. And because it's spinning around and around, if we have a loop of wire somewhere nearby, because that's like a spinning magnet and a loop of wire very close by, and as the flux lines from that little vector m, and collectively across our whole sample, all those flux lines, they're changing with respect to the loop of wire, and so we end up with an induced current in the loop of wire, proportional to the rate of change of flux. And so this is why it's a squared term, because this magnetization m is rotating at omega, and so it can be represented as mxy is m. So the mxy in the lab frame is mxy in the rotating frame times e to the I omega t. And so when you differentiate that to get the rate of change of it with respect to the coil, you end up with an additional omega term coming out the front. So that basically gives us a second term proportional to the magnetic field. So that's why the signal goes like the main field squared. But that's kind of in the details. The main thing is that the main thing I really want you to get away from this, take away from the slide, is that the only thing we can detect is the mxy term, and it's considered to be a complex signal. Okay, so this is just summarizing how the magnetization relaxes back towards M0. It typically relaxes, according to this is a phenomenological equation. What we see is a decay curves basically. So whenever you start, it basically relaxes along a curve like this. So it's gradually asymptotically approaching the original M0 value. Okay. So another way to think about that, so that would be represented typically by this kind of equation, but I actually prefer this equation here, which says that if you've got some kind of magnetization level set up already, if you've set up the magnetization to some level mz of 0, and then you just let it go and see what happens, is your initial contrast, which is typically represented by mz of 0, decays like e to the minus t upon t1. So if you've encoded any information into this mz term somehow, then that information is lost at a rate of e to the minus t upon t1. And then all this magnetization here is just new, contains no useful information. It's basically just fully relaxed magnetization, and it's clean, it's not encoded in any way. Okay, so if you need to do an experiment, you need to do it within a time period t1, because otherwise all your prepared magnetization is gone. On the other hand, if you want to kind of get rid of all the stuff you've done before and have no history of the previous experiments you've run, if you wait long enough, this will basically, this term will go away. This is how long it takes for the previous experiment to be lost. And this is all clean magnetization ready to go again. Okay, here it is looking at it again. You can see that basically the T1 time constant is time taken to recover to 63% of M0, and it basically asymptotically recovers towards M0. On the other hand, MXY, which is the part where we actually get the signal from, decays like T2. And basically anything that causes is a source of T1 relaxation is also a source of T2 relaxation, but T2 also includes other sources too. So the signal will generally die faster than MZ regrows, because T2 is pretty much always less than T1. Okay, so that's the rate at which we lose our signal if we try an image with it. So when we've excited our signal and tipped it into a transverse plane, we lose it at a rate T2. And in fact, we actually lose it a bit faster than T2, because T2 represents the irreversible loss of MXY. But it turns out that because we have an inhomogeneous field, different parts of our sample will get out of phase with each other. So in other words, if we had a sample with spins in different places and they experience different magnetic fields, some of those will be processing at slightly higher frequency, and all these different spin vectors will kind of gradually get out of phase with each other, and the signal will decay like this. And so instead of having T2 relaxation only, we'll end up with actually a greater relaxation rate, and this is known as T2 star rate. So that might seem to be a bad thing, But actually it's the source of our fMRI signal, because basically, as Vinay showed yesterday, when you have the deoxyhemoglobin, it causes those inhomogeneities and it causes the signal to decay faster than it would do otherwise. So it's actually the source of our contrast. So that's kind of a good thing, actually, even though it's kind of represents the loss of our signal. And in any case, the T2 star, to some extent, can be mitigated because you can apply something called a spin echo, where you use another RF pulse, but this time basically flips all the spins over. So that once they've started dephasing like this, you can apply another RF pulse that takes this entire disk and rotates it, flips it over, so that it goes. And so then, if the spins continue to process, they'll kind of refocus in along one direction. So you can mitigate some of those T2 star effects with spin echo pulses. Okay, so that's the basic NMR stuff. Now I'd like to discuss kind of image formation techniques, and in particular the main thing for spatial localization, which is gradients. So just to summarize that again, basically we have our main magnetic field B0, and of course we have omega equals gamma B, which is my favorite equation of the day. And supposing we now can superpose what we call a magnetic field gradient. And what that means is it's an additional magnetic field which varies in space. So it's a magnetic field. The magnetic field we add is still along the z direction, but it may vary in space. So the magnetic field vectors are all still pointing along the z direction, but there's more of it, but it's a stronger magnetic field on, say, the right than on the left, or at the front of the magnet than at the back, or the top and the bottom. Right? Then let's take one that goes from left to right. So then you'd have an additional magnetic field here, like this, and so you'd have some additional magnetic field, and it would basically just add up on top of the existing B0 or subtract from the existing B0 here, and there's not much effect in the middle. Okay, so these kind of magnetic fields are what make the sound in the magnet. It's when we pulse them on and off. We can turn them on and off. They're quite small magnetic fields in comparison to the B0 field. They're like about 1,000 times smaller. And basically they just slightly affect the frequency of the spins, so that if on this side, if you have this gradient on, the spins would be spinning a little bit faster because omega equals gamma B, and then here they'd be spinning a little bit slower, but it's just kilohertz, not megahertz now. We're talking about this additional frequency. So here, for example, is a magnetic field with a gradient, a magnet with a magnetic field gradient added onto it, kind of exaggerated. In the x direction. So as you can see, the field lines, the field direction is still along z, but it's just a stronger field on the right than it is on the left. And of course you can put it on the other way, or you could have one that goes in the z direction. This is a z gradient, so it's a stronger magnetic field at the top of the magnet and the bottom, and vice versa. And you can put both on at the same time, and you can obtain a kind of field like this, where it's very small in this top corner and it's really big down here, and it kind of varies linearly across the space. Okay, so that gets us around to slice selection. So let's say I'm lying in a magnet, and I'm basically I'm interested in acquiring a slice about here, where this blue line is. So relative to the center of the magnet, this is at some position z here. If I turn on a magnetic field gradient gz, I find that this position here has a very specific frequency. Actually, and due to the slice thickness, actually there's a complete band of frequencies. Depending on how thick my slice is, it's a wider band or a narrower band. And then, so what I can do is I can now choose to design a pulse. I have one of those B1 pulses I was using before, but if it only has but if it only contains a mixture of the frequencies present in this band. Okay, so I take, instead of applying the pulse at the original B0, I apply it at an offset frequency B0 plus omega plus delta omega, where delta omega is the appropriate gradient offset. And in fact, it's not just one frequency, it's a kind of a mixture of a band of frequencies. And what that mixture of band of frequencies gives you is a pulse shape that looks something like this, which is a sync pulse. And what that band will do is, because it's NMR is a resonant phenomenon, unless you hit it pretty much bang on the frequency you want, the spins will ignore you. So basically, if you hit it with this band of frequencies, all the spins that are inside this plane represented by this line the plane that goes into the board, will be flipped over just like they were before when we were just dealing with that bulk magnetization vector. Okay, and all the spins out here will be unaffected. And the reason they're unaffected actually is basically because they're spinning to a different frequency. And remember that B1 is needing to go round kind of with the magnetization. And so basically if it's at the wrong frequency, what happens is initially it's kind of at a certain position with respect to magnetization, and then after a very short time it becomes out of phase with it. And so all these, the effect of that field kind of cancels itself. So it really only affects the magnetization inside that band, and it has very little effect anywhere else. And so basically just excite into a transverse plane spins in this slice plane. Okay, when we do that, what we end up with is, so here's our sync pulse, and this is what MX and MY look like. And they're a little bit messed up because there's MX and MY here, but if we have to apply a little rephasor gradient, and it basically gives us a nice slice along the Y direction. Okay, not Y direction in space, the Y direction in this transverse rotating plane. So, and what we've done is we've effectively excited just this narrow band of frequencies, and that's basically because of the gradient. That's a narrow band of spatial positions. So this is basically like looking at our slice end on, and so we've just excited the things into the transverse plane from that slice, and all the rest of the tissue is still along MZ. And because you only collect signals from MXY, you won't get any signal from them. You'll only get it from the slice you've excited. Okay. Next thing that Vinay also discussed was a kind of gradient echo pulse. And so here we basically, so having excited our slice, we now apply a gradient in an orthogonal direction. And we have a kind of, we can consider it to be, if we apply a small gradient pulse like this, oops, what will happen is our spins will dephase. Then, if we turn the gradient the other way around, it should cancel that effect because it's all just rotation. So if you apply the gradient in the other direction, they'll spin back, and when you've got the same amount of gradient pulse on this side, you find it as an echo signal, and this is called a gradient echo. And this is usually how this is presented. And here we have the, of course, we've got to do this in the T2 star time, but so here's the initial magnetization tip down. We apply this gradient dephaser pulse, and it dephases all spins, and then we apply this refocusing gradient, and it refocuses them into an echo. Okay, and this is usually how MRI is often described this way. But I prefer to use this case-based formalism. So once again, let's talk about the imaging gradient. The imaging gradient, as we noted before, can be applied in any direction in space. So we can have the X component, the Y component, I should say Y and Z component. And of course, these are all, as I said before, they're actually like magnetic fields in the Z direction, but they vary in X, or vary in Y, or vary in Z. Okay. Then, if I've got a spin at if I've got some tissue at a position X, Y, Z in the magnet, then the actual frequency offset I should get is gamma G dot R, which should be gamma here. Right? It's basically the Gx times the X component, the Gy times the Y component, the Z times the Z component. Okay. So looking at that in a little picture, let's consider this little green blob of tissue. I put an X gradient on. It spins an additional, it spins at the Larmor frequency plus an additional frequency offset due to the X gradient here, as shown here, depending on its position in the X direction. If I then later on put a Y gradient on, same blob of tissue, it's at a different position in the Y direction. So it has this other offset frequency here. So the total phase it accumulates depends on the gradient at a given time, because it's got an instantaneous frequency here given by gamma G dot R. Okay? But the phase it accumulates is basically the integral over time of G dot R. Okay? And then if we consider enlarging that to the whole slice, to the entire object, so we consider all the green, consider the tissue, the whole slice to be made up of different little green blobs of tissue like this, and we add them all up, basically, that's what this integral is doing. We end up with something like this. And now by defining the term in square brackets to be k of t, making this term here to be k of t, which is basically the term in the square brackets, we end up with an equation like this. Okay, so now we just write our signal as k as a function of k, as being this is how many spins I've got times by this dephasing term, and this is basically a Fourier transform. And the Fourier transform can be inverted, and so it allows us to calculate our spin density from the signal we acquire. Okay, so that's all the maths, and I just want to get it all out of the way in one equation. So if that's too horrible, I won't do any more of it now. Okay, so what does this really mean? Okay, so blatantly having ripped off the nice slide, here we have, this is our Fourier transform pair. Okay, so here's our image, here's an image, and here's its Fourier transform. Okay, and they look kind of different from one another. Typically what it is, a Fourier transform typically relates something, they're considered to be two corresponding domains. They're reciprocal domains to one another. So one might be frequency and the other one might be time. One might be space and the other one might be spatial frequency. So here we have space. This is a row of R is the spatial map of our water magnetization, and S of K is our K space. And so this is basically spatial frequencies, as Vinay discussed before. So here's a point near the center of K space, and in spatial, so this is in K space. Here we have a point near the center of K space, just slightly offset in the KY direction, and you see we have this kind of low frequency modulation of the space in the Y direction. If this had been off in the X direction, it would have been a low frequency modulation of space in the X direction. Here we have a point near the edge of what I'm calling the edge of K-space. Of course, K-space goes on forever, but near the edge of the K-space field of view we're interested in anyway. And you can see it represents a much higher frequency in physical space. So what does that really mean in terms of our actual imaging? What does this really get boiled down to in our imaging? Well, when we excite our tissue, when we do our initial excitation, either slice selective or not, we can think of ourselves at the middle of K-space. Okay? So this corresponds to no phase across the image. Here we have this green line, it's completely flat. But it's basically all the magnetization right after excitation should be pretty much in phase with one another. There's no phase dispersion across it. Okay? If I move in K-space by one sample, these are the sample points I'm going to collect. So if I move by one K-space sample, what that does is it means I put a gradient on. And what that gradient has done is it's increased the frequency on the right side of the image and reduced it on the left side of the image. And basically it's caused phase to accumulate on the right and to be a little bit less on the left. And I end up with a phase dispersion across my field of view of exactly 2 pi. And if I advance another K-space sample, I end up with 4 pi across my field of view. Note that nothing much happens in the middle of my field of view because the gradient has very little effect there. Okay? By the time I get to the edge of K-space, what I've got is I've got pi across my what I consider to be a voxel now. That's effectively, by calling this the edge of K-space, I've essentially defined that this is what a voxel is, and it's where I have pi phase dispersion across a voxel. So that seems a bit odd. Why isn't it 2 pi? But the reason it's pi is that by the time I get to the edge of K-space, if I had that means I've got kind of one voxel has like a positive lobe of a sine. Think of it like a positive lobe of a sine, and all that integrates up, and it's kind of all, some of it's kind of pointing off to left and right, but it's all basically pointing forward, right? If I take the voxel next to it, it's all kind of a negative lobe of a sine. So there's some of it pointing left and right, but it's kind of all of it's pointing downwards. So it's basically, if you go any further than the edge of K-space, what happens is you're starting to lose signal across, significantly lose signal across that voxel, because you've got multiple phase twists. You'll have multiple twists within a voxel. So basically what the edge of K-space is when you've got pi phase twist across a voxel. I don't know if that's helpful, but that's how I like to think of it. Okay, so how does that help us in terms of imaging? Well, if we come back to this equation here, this is our K-space imaging equation, and this is our what the K is with respect to the gradients. Okay, so the gradient, this K is really just the integral of the gradient with respect to time. So we can think of this like a space. We can think of G as kind of like a velocity, and we can think of K as a position, because then basically if K is a position where we want to go, where we want to be, then G is our velocity of how fast we're moving at any given time. So G is velocity through K-space. If we have a bigger gradient, we're zipping along here. If we have a slow gradient, we're kind of taking it slowly, and we can apply our gradient in, if we apply a gradient in X, we go this way. If we apply a gradient in Y, we go that way. And if I apply my gradient in Z, I'd be coming right out of the board at you. Okay? And kind of corresponding to what I said before about the edges and the step size in K-space, the sample spacing here, delta K, the intersample spacing is the field of view, defines the field of view, and the edge of K-space defines the reciprocal the pixel size. In fact, it's like in inverse units, but basically the smaller the sample spacing, the larger the field of view. And the further out we go in K-space, the higher the resolution. Okay, so here's our gradient echo again. Here's our excitation pulse. We have this initial dephaser that takes us all the way to the edge of K-space as far as we need to go. Then we flip the gradient over and we read out, and we collect all our samples from one side to the other as defined by the field of view and the pixel size we want. And we collect this echo signal, and then that gives us one line of our K-space acquisition. Now we don't just want the center line, of course. We also want to get the lines above and below it. So if we, so what we can do is we can apply an orthogonal gradient, a GY gradient, in small steps, and we repeat the experiment. Basically, this notation here generally means that we repeat the experiment over and over again, and each time we can step it one step further out in space, so that we obtain, when we put it all together, we can start out on our first excitation. We can dephase it right to the bottom of this and play our gradient echo and come down here and read out, and then the next one's over here, the next one's up here, the next one's up here, and so on. And each time we're collecting a different line in the K-space. We take all this data, we put it through the Fourier transform, and hopefully we get an image out the other side. Okay? Seem reasonable? Yeah. Okay. So what else can we do? Well, if we want to get a bit more ambitious, rather than just collecting one line and then having to wait for everything to relax and before we go again, we can try and read out the whole thing in one go. And this is the echo planar trajectory for which we do all our fMRI with. So basically, this one, we excite, we have a small dephaser gradient which takes us to the edge of K-space. We have a kind of a large lobe in what I've called G2 direction here, which dephases you to the edge of K-space in the Y direction. And then we read out in the X direction, takes you along here. And then there's a little gradient blip here that pops you up to the next line, read out again, up to the next line, so on, back and forth all the way along the boost orthodonic trajectory. Okay, and at the end of it, hopefully we've got the whole K-space. Now, so that's a pretty efficient way to collect your image if you want to do it. A couple of things that are kind of interesting about this is that, of course, compared to the previous one, where all these lines are kind of acquired at the same time, equivalent, all the data is kind of acquired at the same time relative to the RF pulse. In this acquisition, each line is acquired a little bit later in time. And so it's kind of because as we discussed before, or Vinay discussed before, a lot of the basic contrast of our image is determined by the central K-space. It's kind of nice if we can arrange to travel through that central K-space region at a time when the contrast is ideal for us, which in our case is the time when the deoxyhemoglobin and the contrast between the deoxyhemoglobin and the oxyhemoglobin is the greatest. So that's typically about 35 milliseconds or so, I think, at 3T, and maybe like 27, maybe, looking for. yeah, at 70. So you've got about, basically after the excitation, you have about 35 milliseconds to hit the middle of this. And because you've got to scan left and right, that means you either have to have pretty significantly big gradients, or, well, you won't make it to the middle in time, basically. It's quite demanding on the hardware to get that to work. Okay, and so while we're at it, we can actually do other things too. You can imagine all kinds of other. This is a very early echoplanar trajectory that was proposed. You can imagine doing spiral imaging. You can. This is of course the regular echoplanar, pretty much, and then this is if you've put a sine and cosine weightings on your gradients, which might be a little gentler on the hardware than the sort of hard switching from left to right, left to right, left to right. But actually spends a lot of time at the edge of K-space, so it's probably not such a good idea. Okay, so what are you going to do if you want to get to higher resolution? Because as we discussed before, when you do this, the need to switch the gradients backwards and forwards limits how far you can go on each readout and how many such readouts you can do before you get to the middle. How can we get to higher? How can we accelerate the acquisition? So that's what the next section is basically going to be about. So improving it, if we go faster, the idea is that we can either improve temporal resolution, maybe get improved coverage. We can reduce the effects of that long readout time that the EPI has, helps reduce the distortion in the images. Okay, so I'm going to talk about a couple of methods to do that. So one of the earliest acquisition techniques to actually avoid when gradients couldn't operate very quickly was just simply keyhole imaging. So what this would basically do is taking this notion of the K-space, much of the K-space contrast is in the center of K-space. Much of the image contrast is in the center of K-space. Basically what people would do is they would basically acquire a band in the middle of the data set over and over again. They might acquire the edges of K-space once or infrequently, and then basically substitute different chunks from the center of K-space over and over again and repeat. And it's not really a very good way to do it. The images you're really getting are like this, and then you're kind of trying to enhance them by using some less dynamic information here. But really what you're dealing with is data that looks like this. So it's not really great to do that. But it's still done. So another way to get acquisition acceleration is to note that if you can think that your underlying image is real valued, if you think that your image is going to be like a real valued image, then the K-space, in theory at least, is supposed to have conjugate symmetry. So a sample over here in K-space is supposed to be the complex conjugate of the corresponding sample on the diagonal opposite corner, okay, as represented by this equation here. So in principle, if you had this one, you could probably synthesize that one. Okay. In practice, because there's always some kind of background phase effects due to the receivers coils themselves, you actually need a little bit more data than just half the K-space. But if you acquire a little bit more than half, you can usually make a fairly good job of doing that, unless you happen to have phase in your image. So two ways to do this. One is to what is called partial echo or minimum TE, I think, on GE, and called asymmetric echo on Siemens, is to skip this part of the K-space and just acquire this part. So if these are your readouts, they would just be acquiring very short readouts. And that effectively gives you a very short TE, which is sometimes very useful if you've got something with a very short T2 star. Another way to do it is to just do less lines in K-space. So you're basically needing less TRs to acquire your image, or less lines in your EPI readout. So that's another way to go if you want to do that. Okay, now I'm going to move on to parallel imaging, which is kind of a much more modern way to do these things. And this basically becomes possible because our scanners today have many receiver coils. Okay, so there used to be one, a member of 4, a member of 8, and now basically all systems are coming with 32, 64, 128 coils. Okay, so, and what this boils down to is that typically what you have is this is a classic simulated brain phantom. And basically, so as though you've got all those loops of wire that collect the signal, you've got a whole lot of them instead of just having one around the brain. And I've got 6 here. You've typically got, as I say, between around 8 and 64. Most of our scanners have 32. just to give you some idea. Okay, so it turns out that each of these coils has these are only used for signal reception, but not, there's a separate big coil that's used for excitation. So this is just for the signal reception part. So it turns out that each coil has a distinct spatial profile, sensitivity profile in the space. So here's the one from down that corner, and it's, I mean, not surprisingly, it's much more sensitive to spins that are near to it, and much less sensitive to things that are far away. And so, because this is basically the B1 field lines that would be induced if you put a current around this coil, because it's kind of reciprocal. I know we're detecting the magnetic field rather than creating it, but it works in reverse too. So you can think of it as just having this kind of pattern, and because the field lines are stronger close to the surface, which incidentally is where we're mostly interested in looking, you get a much stronger signal there. Okay, and so this potentially it's kind of like a gradient. It gives us kind of additional degree of freedom to do our spatial encoding. So if we consider a coil here, and then let's consider a coil on the opposite side. Okay, so now we've got these two different spatially encoded signals from each of these two different coils. We have to capture them, record them separately, and work with those two data. So now we're working with much more data because we haven't just got two, we've got 32. So instead of collecting all those data, we now have to collect all those and handle them all separately. Okay. So far, what does that get us? It basically has us collect two images which are not very good, and we have to find some way of combining them. But let's look at our case-based sampling pattern. So this is our standard acquisition that we were doing before, and this is our 1 over field of view. Okay. So what happens if we basically skip half the lines? So there we go. We skipped half the lines. We're just doing all the even lines now, say. As a result, our case-based step has doubled. That means our field of view is half what it was before, because it's 1 over field of view, right? So if we double that step size, this field of view becomes halved in the phase encode direction. Okay. So the images we were getting before, the image from coil 1, which is the one down at the bottom corner, now looks like this. And the image from coil 2, which is one up in the top corner, now looks like this. And hopefully those look different. Do they look different to you? It's hard to tell from this angle. Okay, good. Okay, so, and this is a side effect. This is a direct side effect of only acquiring half the lines. But then they're both folded over. But they're folded over and they're kind of different, right? So if I look at the image in coil 1 for the green dot, so this green dot is supposed to be the same position in space in the image, same position in the image, right? Because it's folded over exactly by half the field of view, what I end up with is that this image here in the first image is some weighting factor times the IXY of my original image here. So if the green dot was there, there's some weighting factor of that, W11 times that, plus W12 times the position that is half a field of view down, so the position that's down here. So it's a kind of a combination of data from here and here, added up in some linear combination. Okay? Am I going the right way? Yeah. And similarly, on this one here, it's the signal I'll get from this pixel is a combination, a different linear combination of the same two pixels, but with different weights, because the weights depend on the coil, the signals from that coil, and that depends on that coil profile, which we were looking at before. And so this now looks like a system of linear, it's like a system of simultaneous equations. And I've shown it here with two equations in two unknowns, but in practice we have like 32 equations or 64 equations, depending on how many coils we have. And we may have two unknowns, or we may have three if we do 3 times acceleration and so on. But basically it's a straightforward linear system of equations. And if you prefer it, you can write it in a matrix form where the signal is the encoding matrix times the image. And you can basically invert that system by taking the pseudo-inverse, because this is in practice this isn't a square matrix, it's a rectangular matrix, but you take the pseudo-inverse and you can get the image out directly from that. So That seems quite nice because it basically means that we can now acquire the image in half the time, or a third of the time, or a quarter of the time, depending on how much we want to push that skip and how wide we want to make that skip in space. The main problem is that this is not really an orthogonal matrix, so when we invert it, it can cause serious noise amplification, and so there's a whole huge body of work on trying to control that noise when you do this inversion. But basically, this is how parallel imaging works using what's called the sense method. And the example here is r equals 2, that's the acceleration factor. There is an alternate method which is very commonly used in Siemens systems, and is actually probably the most popular method today, which is instead of working with the image domain, I like explaining to the image domain because it kind of makes more intuitive sense. But you can also do essentially the same thing in the k-space domain. And what you have to do is basically acquire, what this boils down to doing is interpolating and trying to figure out what this green dot, missing green dot sample is from its immediate neighbors. And what happens is you slide this box around. Once you know how to do that inversion, you can slide the box around and you can reconstitute all the missing data from every line. And this method is known as grappa. And the main problem in all these methods is that basically you have to collect additional calibration data in order to do the inversion. They're fairly much equivalent to one another. There's certain advantages for grappa in certain situations. But basically, the main thing is you have to acquire additional calibration data, and you either do that during the scan itself, or you have to acquire it ahead of time. And that's basically, in sense, it's basically you need to know what the shape of that roll-off is for each coil. And in grappa, you have to be able to work out what this kernel is. This is basically a convolution kernel. And it turns out that it's kind of interesting, but it's pretty much the same kernel everywhere in space. But you have to be able to work out what that is, and you do that by acquiring additional data ahead of time in your scan. Okay, the last acceleration technique I want to mention is something called multiband, and it's also known as simultaneous multi-slice data acquisition. And I'm going to return to this idea of slice selection, which we talked about much earlier. Again, if you recall that we put a slice gradient on what's called the slice gradient, and we excited a band of frequencies around this center of this slice. And how wide that band of frequencies is determines how thick the slice is. Okay, so supposing we wanted not just to acquire one slice, but we decided we want to acquire multiple slices simultaneously. Well, here's multiple slices. What if we were basically just to take a band of frequencies here, and a band of frequencies here, and a band of frequencies there, and add them all up, and use that as an RF pulse? Well, surprisingly enough, it kind of works, at least if you can keep these gaps reasonably large. So typically about 3 or 4 slice widths apart. So you can do that, and you can basically excite multiple slices all into the transverse plane at the same time. So that seems good, right? So, so what's the problem then? So the problem then is that, so we have all these slices excited simultaneously, but when we read out in along the x and y directions, and the readout and phase encode directions, all the slices get collapsed together directly. And we end up, when we read out our image, we basically end up with this kind of superposition of all the images. Basically, it's basically a projection taken along this line. And you get the sum of all these 4 positions together. But we just worked out that with the coil profiles, we can separate overlapped images. So basically what multiband imaging is using the coil profiles, just like we did in sense and grappa, to separate these slices into their constituent parts. There's one other little technique for improving this, which is that they use this method called Kaipi, which is a trick that basically slides consecutive. Each image is pushed slightly apart further by applying basically a gradient along the z direction between successive acquisitions. So what that does is it basically causes the images in each next slice to be shifted up in relative to the one before. And what that does is it means that spatially this pixel is now even further away from that pixel than it was before. And that helps improve the condition of that inversion matrix when you do that, when you try and separate that simultaneous equations. It improves your ability to solve that simultaneous equation system. And so that's improved something called the G-factor. You'll hear people talking about that. And what that boils down to is it makes it less noisy. Okay, so before I wrap up, I just wanted to say a couple of things about controlling the image contrast. Imaging sequences that you make basically have some kind of intrinsic contrast, because the contrast is typically determined by when you sample the center of K-space. So typically for a gradient echo, that's going to be pretty soon after you play the RF pulse. There's not been a lot of T2 star dephasing. If you had a spin echo sequence, it would be shortly after. It's still a pretty short amount of time. If you do an EPI, it's a much longer amount of time, and so you end up with a lot more T2 star weighting, which is great if you're doing fMRI. Okay, but how can you actually control the contrast? Well, a nice way to do it is to use something called the contrast preparation module, which takes us all the way back to the beginning of the discussion when I was talking about MZ, and the fact that that MZ of 0 decays like T1. So what you can do is you can encode some contrast into the MZ before you start imaging with it, and then you can play with it during the imaging time and take a picture of it. But you can kind of store some magnetization ahead of time, and this can be useful for doing things like fat saturation or flow preparation or diffusion preparations in some situations. So, I mean, MP-RAGE is kind of an example of this. So MP-RAGE is an anatomical sequence, which is commonly used to get your anatomical image that you superimpose your fMRI excitation maps on. The MP-RAGE is a 3D acquisition that is typically used to get good gray-white matter contrast. Okay, and this is taken from the original paper. So basically what you have here is you have an RF pulse here. There's an inversion pulse, and what it does is it takes the magnetization initially along Z and flips it upside down. Okay, then we wait for a period of time, and then we can do we can play an imaging sequence here that samples that inverted magnetization and collects a line of data when the gray-white matter contrast is maximal. Okay, well that seems straightforward, but you still have to play this over and over again. But the trick is that you basically apply the inversion pulse only once, and then you read out a whole lot of times for each inversion. And this means you don't have to wait don't have to wait for full magnetization recovery. You can basically collect a whole lot of these imaging readouts, one after the other. And then finally, when you've kind of used up all your prepared contrast, because you've kind of used it all up, basically, then you can just wait and you can restart the sequence again. Okay. So what this does is it basically allows you to acquire a nice image in basically about 5 minutes if you do use this sort of method. Finally, I just want to say a couple of words on SAR and gradient stimulation. So these are the two of the main concerns for safety in the MRI system. The SAR is basically a measure of a rate at which the energy is absorbed by the subject, and all that energy really doesn't come from the main magnetic field or the gradients. It all comes from the RF that we apply. And while we're here, we should probably mention that multiband imaging significantly increases the SAR because you've got all those superimposed magnetic pulses being played at the same time. Peripheral nerve stimulation, so what SAR does is it basically deposits energy into the subject. So it'll cause them to warm up, and there are limits on how much you're allowed to heat up the subject. Peripheral nerve stimulation is caused by the rapidly changing magnetic fields, which are typically our gradient fields, which are inducing electric fields in the tissue and causing stimulation of nerves. And when this happens, basically the subject may feel some tingling, or they may feel pain, and if it's sufficiently high. Typically, people will find it kind of like a strange tickling sensation, and the scanners are supposed to have limits built in to prevent this from happening, but occasionally you do find peripheral nerve stimulation, so be aware of that. Okay, some other stuff which I'd love to talk about but ran out of time is discussion more on artifacts, motion suppression, diffusion imaging, and system engineering. But I guess unless I can persuade Peter to have more talks, and it's already quite a long series, I guess we don't get around to that. Maybe somebody will cover it in future lessons, future lectures. Okay, well, thank you for your attention. Yep.
I'm curious about whether all of these kinds of sequences, for instance, multiband, can be implemented on any scanner, or does it really take a lot to get these sequences on a given scanner? How does that?
I mean, so we're about to have. Are you meaning for any given sequence, or are you? I mean, so for example, MP-RAGE is a 3D sequence, so you would never really use multiband with MP-RAGE, right? But for fMRI, I think we already have SMS on the. Have we got it already on 3TD? Didn't I? Yeah, I think we have it on 3TD on the Skyro already, and we're about to.
A lot of people who are here for the summer, one of the things when you learn all these is that what standard versus what really takes a lot of work from physics to implement.
Right. So hitherto, basically, doing SMS required you to pretty much write your own sequence or go to one of your colleagues at another site who've already done it and bring it in. And the tough step wasn't so much the writing sequence even; it was more getting the reconstruction to work right. I mean, it's quite a lot of effort to make it work well. Okay, but in the next release of software on GE, for example, which we'll be getting in probably a month or two, it will have an SMS diffusion included. Likely, Vinay and I will take that and try and make it do regular, without making any promises. We'll try and make a research sequence that can do regular fMRI with it. And then it should reconstruct on the scanner, because the big downside of writing your own is typically it won't reconstruct on the scanner. Well, it might do on Siemens, because I'm looking at Renzo. But on the G, it would have been that you have to take your data away, and it will take an hour to reconstruct a slice, or So, but this will have it, and hopefully it'll work well, right? So we're getting to the point where that's state of the art of what you can buy. Yeah. Okay. Well, I'm around. If you think of any questions later, please email me or come find me. I'm happy to answer any questions. Okay. Thanks.